This number, 1.666, means my model is worse at predicting text than a very basic algorithm that knows almost nothing, and this was the first machine learning model I had ever trained in my life. OpenAI is running a competition called Parameter Golf, where the goal is to train the best possible language model that can fit inside just 16 megabytes, which is smaller than most MP3 files you have on your phone, and the way they measure quality is with something called bits per byte, which just means how efficiently your model predicts the next word in a sentence, and lower is better. And the current best score on the leaderboard is 1.03, and there are over 1,200 teams competing. Before I get into what happened, let me spend 60 seconds explaining what a language model actually is, because it made this whole competition make a lot more sense to me once I understood it properly. A language model is basically a system that has read an enormous amount of text and learned the statistical patterns of which words tend to follow which other words, so if you give it the sentence "the cat sat on the," it doesn't know what a cat is. It just knows that in millions of sentences the word mat or floor tends to come next, and it assigns a probability to every possible next word. The better your model is at predicting the next word accurately, the lower your bits per byte score, and the smaller you can make the model while still being good, the more you win this competition. That's it, that's the whole game. 16 megabytes, best predictions, lowest score wins. I had no machine learning background and no access to the kind of hardware the top teams were using, so I decided that instead of trying to become an ML engineer in 4 weeks, I would build a team of AI models and use each one for what it's actually good at, and together maybe we could punch above my weight class. Claude handled strategy and decision making, GPT wrote the training code, Gemini read through all 2,200 competitor submissions so I didn't have to, and Grok, well, we'll get to Grok. One more thing you need to understand before the story makes sense, which is that the competition runs on 8 H100 GPUs. That's roughly $300,000 worth of hardware that can train a model in 10 minutes. And I'm running a single consumer GPU sitting on my desk called a DGX Spark, which means my model takes 4 hours to do what competition hardware does in 10 minutes. And I knew this going in, and I entered anyway, because I wanted to see how far good strategy could close the gap on bad hardware. Before I get into what happened week by week, let me show you what this actually looked like in practice, because the workflow was genuinely different from how most people think about using AI tools, and it was not just asking ChatGPT questions in a browser tab. Claude Code was SSH directly into my GPU over a terminal, running training jobs, evaluating checkpoints, building the pull requests, doing file operations, and I was essentially giving it a mission and checking in on it the way you would check in on a junior engineer. And most of the time it did exactly what I asked, and occasionally it made a judgment call that was better than what I would have done myself. The first thing that went wrong happened on day 2, when I asked Grok to evaluate one of my early model checkpoints and report the bits per byte score back to me, and it came back with a score of 0.00000, which if you remember means the model is perfectly predicting every single word in the English language with zero error, which is not only impossible for a 16 megabyte model, it is impossible for any model that has ever existed, and Grok reported it completely confidently with no caveats, as if it had just witnessed a miracle and decided not to mention it. I went back and ran the evaluation myself, and the real score was 1.666, which is worse than the baseline, which means Grok had not hallucinated a slightly wrong answer. It had hallucinated the exact opposite of the truth, and presented it as fact, and this taught me something important about using AI models for technical work, which is that confidence and accuracy are completely unrelated, and you always need a ground truth you can verify yourself. After firing Grok, I restructured how the team worked, with Claude acting as the project manager who designed experiments and decided what to test next, GPT writing the actual Python training scripts, and Gemini going through the competition repository and summarizing what techniques the top teams were using. And this division of labor worked surprisingly well, and by April 13th we had our second model submission at 1.397 bits per byte, which was meaningfully better than our 1.666 start, and it involved better hyperparameters, a technique called exponential moving average to smooth the training, and running 3 separate random seeds to make sure we weren't just getting lucky. One of the things that made this experiment feel more like real engineering than just vibes was that I had a Streamlit dashboard tracking every single run, every model version, every hyperparameter combination, every bits per byte score, laid out in charts and heat maps so I could actually see which directions were working and which ones were noise, and this turned out to be essential, because without it, the forgotten checkpoint story I'm about to tell you would have had a very different ending. Around this point, I had spent 3 full days building something called an n-gram backoff cache, which is a technique where you supplement your neural model with a lookup table of common word sequences, and on paper it looked promising. And Claude had designed a 27-cell experiment grid to test every combination of settings, and I set the whole thing running overnight before I went to sleep. And when I woke up at 3 a.m. to check the results, which, yes, I was waking up at 3 a.m. to check model scores, this is what the competition does to you. I found that a much simpler technique I had thrown into the grid almost as an afterthought, called sliding window evaluation, was outperforming everything I had built in those 3 days by a significant margin. 3 days of work dominated by a parameter I changed in about 4 lines of code, and this is something no tutorial prepares you for in machine learning, which is that the thing you spent the most time on is frequently not the thing that matters, and the only way to know is to test everything and let the numbers tell you the truth. By April 19th, I had a version I was ready to submit, sitting at 1.364 bits per byte, and I asked Claude to run a final audit before I committed the pull request. And this is the part of the story where I am genuinely glad I did not skip that step, because buried in my checkpoint directory was a file from April 11th that I had completely forgotten about, a model I had trained early on using int6 quantization, which is a technique for compressing how numbers are stored. And when Claude evaluated it with the sliding window technique I had just discovered, it scored 1.310 bits per byte, which was 5% better than the model I was about to submit, and I had just been sitting on it for 12 days without knowing. I almost submitted the wrong model. The audit caught it. This is now a permanent step in every workflow I run. So the final submitted score was 1.310 bits per byte, which is genuinely not bad for someone with no machine learning background running on a single consumer GPU competing against teams with access to 8 H100s. But I want to be honest about what 1.310 actually means relative to the leaderboard, because the current leader is at 1.03, and that gap of 0.28 is not a gap you can close with better strategy or smarter prompting. It is a hardware gap, and the reason is simple. More compute means more training steps, and more training steps means a better model, and I was running a bicycle in a car race and I knew it going in. What I could control was how intelligently I used the compute I had, and I think the multi-agent workflow genuinely extracted more value from my hardware than I could have alone, and that is actually the more interesting result of this whole experiment. So here's what I actually learned from spending 4 weeks competing in an OpenAI machine learning challenge with no ML background, using a team of AI models as my engineering department. The first thing is that different AI models genuinely are better at different tasks, and Claude was better at strategy and synthesis, and GPT was better at writing code, and Gemini was better at processing large amounts of text, and treating them as interchangeable as leaving performance on the table. The second thing is that the scientific method matters more than intuition, because every time I trusted my intuition about what would work, I was frequently wrong, and every time I ran a structured experiment and let the numbers decide, I was frequently surprised. And the third thing, and this is the one I keep thinking about, is that the judgment calls are still human. When to stop testing and ship, when to throw away 3 days of work, when to run one more audit before submitting. The AI team could execute, but it could not decide. That part was still mine. I want to be clear about something before I wrap this up, which is that I did not enter this competition expecting to win or expecting to get recruited by OpenAI. And I think that framing is actually important because a lot of content about AI tools right now is built around the idea that AI can make anyone competitive at anything instantly. And what I found is more nuanced than that. AI can dramatically compress the learning curve and it can extract more output from whatever resources you have, but it cannot manufacture compute that doesn't exist, and it cannot replace domain expertise overnight. And I think being honest about that ceiling is more useful to you than pretending I nearly cracked the leaderboard. What it can do is let someone with zero ML background train 4 model versions in 4 weeks, run structured experiments, catch their own mistakes before submission, and end up with a working understanding of a field they knew nothing about when they started. And for my purposes, that is actually the more valuable outcome. Submitting to the competition meant opening a pull request on the Parameter Golf GitHub repository, which at this point had over 1,200 other submissions from teams around the world, many of them from people with actual ML research backgrounds and access to professional compute clusters. And I want to be honest that clicking that submit button felt strange, because on one hand I knew the score wasn't going to threaten the leaderboard leaders, and on the other hand I had just spent 4 weeks building something I genuinely didn't know I could build, and that felt worth documenting regardless of where it landed. The competition closes April 30th. The code and the full PR are linked below if you want to look at what we actually built. And if you want to see what else I'm running on this hardware, the next video is already in progress.